In this video, we will discuss about rational algebraic function graph. And we have many shapes of rational algebraic function graph. But for this video, I'm just trying to narrow it into three basic shapes. So if you want to look for more, of course, I will try to share other videos. But for this one, again, only three basic shapes. Okay, so let's start with the first one. The first one is this one. I will give you an example that this is a rational algebraic function because this is a ratio of two polynomials. On the numerator, you can see this is a quadratic polynomial. On the denominator, it is a linear polynomial. And of course, since we don't have any idea what is the shape of this particular equation or function, let's just use the conventional method, which is the best way, using the table of pairs. So while we are not regulated, the domain is not regulated, so let's just use an assumption that we can use any real numbers for your x. So just pick any real numbers for your x and put into this equation and then find the value of fx or the y. And then you get the first pair and then the second pair and so on. And then try to connect those dots. So let's just use, I have already do my homework. So yeah, for this one, I just use these numbers for my x, which is integers between -5 until 5. Again, I can freely use any decimals, I can use any radicals, but for this one, for the sake of the simplicity of my calculation, I will use the integers. And yeah, this all, when I try to substitute, for example, -5 into this equation, -5 into the x, I find that the value of f of -5 equals -4, and so on. And I put -4 into this, I get -3, and I have these pairs. But you can see if we use 2 as your x, put it into this, we have a special condition, which is the numerator equals 0 and the denominator equals 0 also. So we have 0 over 0, which is undefined, or the other term is indeterminate. So we cannot find the value of y when we use the x equals 2. It means on your graph we cannot show a particular any dots, any pair that the when the x equals 2. Okay, so let me just save this for later explanation. Let me just try to put all of the pairs that we have found so far. Okay, -5, -4, -4, -3, and so on. So let me just put into this Cartesian, and this is all the pairs that I have already calculated, except, I mean, I have, yeah, there are some pairs missing, but you can get the idea that actually these dots shapes a particular shape, right? It looks like a straight line. So if we are not very certain about this, of course, I can enhance uh, my, uh, my my search into all of the decimals for my x. So for example, if I'm using -3.5 as the x, and I put into this equation, in the end, I will find that the y equals -2.5. So it's consistently showing that the pairs will form a straight line. So the question is it really true that it will form a straight line, despite that the fact that we know that when x equals 2, there will be no values of y. So this actually is not really correct. But the thing is, in generally, it form a straight line? Because we know that a straight line usually it is a shape of a linear function, right? So if I'm using a linear function for this particular line, actually it refers to a function of x plus 1. But this one is not x plus 1. So let me check further. Is it true that it will form a line? How? Let's go back to the equation. So if we look back to the equation, we can factor the numerator, right? So when we factor the numerator, we have this situation. X minus 2 times x plus 1 over x minus 2. See that we have one factor, x minus 2, which, that the numerator, both numerator and denominator have. So because it's exactly the same, of course we are tempted to cancel it, right? So let's just cancel it. And let's just simplify this function, and voila, we have x plus 1 as your fx. So wow, actually it is a linear function. So that's why you can have a confirmation that actually it shapes a straight line. But the next question is really true that the function of a rational algebraic, this one, is exactly the same with a linear function? Is it exactly the same? Of course not, because if we go back to the table of pairs here, we have this situation. While if we use this particular equation, of course, we can have the straight line safely without any restriction of the domain. So there is something that make a big difference between a rational algebraic function, this one, and a linear function as simple as this one, which is x cannot be equals to, right? Why? Because if we refer back to the original, we cannot use 2 as your x, since it will make the value of y is undefined. So the big difference between this straight line and this straight line is an open circle or a hole right on the position when x equals 2. Why? Because of course we have to really consider that there are no value of y when x equals 2. Therefore, there will be no graph, no pairs when x equals 2. So how to do it? Just use an open circle. Why? Because if you want to look further, if you use, like, for example, 1.5, 1.6, 1.9, and then if we go from the right side, if we want to use 2.5, 2.4, 2.3, getting closer to 2, you will see that it consistently showing a straight line getting closer to y equals 3. So it still forms a straight line, except that when x equals 2, there is no value of y. So that is the difference. So let me just make it simple. The conclusion is this graph with an open circle here is a graph of this rational algebraic function, which is x squared minus x minus 2 over x minus 2. Okay. And if I eliminate that open circle, actually this graph refers to this equation, x plus 1. So the big difference between a linear function x plus 1 and a rational function, which is this one, is just this open circle. This is what makes the difference between a rational algebraic function and a linear function. And how to locate the open circle or the whole this one, just use the simplified equation, which is x plus 1, and use the x equals 2 here, substitute to the equation, so it is 2 plus 1, it is 3. So 2.2 comma 2 comma 3, this is the location of the open circle or the hole. Okay, so that's how you locate the open circle. And this open circle or hole, it is called discontinuity. Okay, because the graph is being discontinued at this specific location, x equals 2. Okay, that's why it is called discontinuity. Since the discontinuity for this one is being removed by canceling x minus 2 and x minus 2, we call it removable discontinuity. Okay, so there will be two discontinuities that we will talk and discuss in this chapter. So this one is the first one, removable discontinuity. It forms like an open circle or a hole, and it comes from uh, these factors that being cancelled because that factors exist on both numerator and denominator. So let me just show you another example to make it clearer. This is another example of rational algebraic function, and this one we have a ratio of two polynomials. On the numerator, a cubic polynomial, and the denominator is a quadratic polynomial. So since we don't have any idea about the shape of this one, let me just use the same thing like before, the table of pairs. Okay, I can use any real numbers for my x and then substitute it into this equation and find the value of fx. So this is it. For this one, again, I use the same numbers, integers between -5 until 5. And again, it's not limited to integers. You can use any decimals, radicals, and so on, maybe except imaginary numbers, of course. But in this particular uh, numbers, I have, for example, -5 and put it into this equation. I have the value of f of -5, -4, and then so forth. And for -3 as my x, I will have an undefined situation again for my fx or y. And if I use 2 as my x, I will have another undefined value for my y. So we have two values of x that will create or results to an undefined situation for your y. So let's save this for later. Let me just try to plot all of the pairs that we have found so far, okay, and put this into this Cartesian. And yeah, actually almost the same like before. It shapes like a straight line. Okay, and if you want to go further and you want to use any other values of x, for example, decimals like negative 1.5 or negative 2.1, it will consistently show the pairs shape a straight line. So let's just assume that this one is a straight line. The next question is, what is the difference between this function with the functions before, since it creates the same straight line, right? So let me just go back to to this equation. Since I know that the numerator is a cubic one, it means maximum it will have 3 factors. And on the denominator, since it is a quadratic, maximum it will have 2 factors if we can factor it. So let's just factor this completely. And in the end, these are the factors. Okay, we can use factor theorem for this one. And look at this, we have 2 factors, x minus 1, x minus 2, and x plus 3, which are the same both on numerator and denominator. Therefore, we can cancel it. And since we can cancel it, we can simplify it into fx equals x plus 1. So we have another situation that the graph will shape a straight line just like x plus 1, except the difference is we have two discontinuities. Okay, since x cannot be, if we go back to the original equation, which is this one or this one, x cannot be 2 and x cannot be negative 3, since it will make the denominator equals 0. That what results the y equals undefined. I mean, it's undefined. So the big difference between these equations with the before, it has two discontinuities. Both one on at this location when x equals negative 3. The second one is when at x equals 2. And again, the same thing, if we want to locate, where should I locate or put the open circle or the hole? Let me just use 2 and then put it into the simplified one. So 2 plus 1, 2 comma 3. So this is the location. And if I put negative 3 into this, negative 3 comma negative 2. So negative 3 comma negative 2. Here is the location of the hole. It means there are two discontinuities because right on this section and in this section, the graph is disconnected. Okay, so that is the difference between this equation with the previous one, this one, because this one has one discontinuity, removable discontinuity, and for x plus 1, it has no discontinuity, but this one has two discontinuities. Okay, so yeah, it is removable discontinuities. Again, since it can be cancelled, it means the discontinuities on your function is removed. Therefore, we call it removable discontinuities, and we have two removable discontinuities, and they are represented by these two open circles or two holes. So don't forget, since if you fail to locate these two circles, it means you are speaking or you are showing a different function, not this one. Okay, you may show this one, or you may show this one. So it depends on the numbers of the open circle or the removable discontinuities. So that is some examples that I want to show you that shapes a straight line. So the conclusion is, if I want to sketch this kind of rational algebraic function, first I need to simplify this as best as I can. Before I simplify it, I need to factor completely both numerator and denominator. So when I try to factor completely and I find some factors can be cancelled, I cancel it and I simplify it. So if the one that being left is a linear polynomial, it means your graph will be a straight line. So just graph this straight line based on the simplified equation, which is x plus 1. Graph it straight with your linear equation technique, of course. And then after you graph it, of course, you have to include all the zeros from the denominators. Because, of course, we are not graphing this equation, we are graphing this equation. Therefore, we cannot include x equals 2 and x equals negative 3 as the domain inside our domain because it is not in our domain, right? so we cannot include on our graph. So we have to present them into an open circle. Okay, so this is called removable discontinuities. So both discontinuities will be located at x equals 2 and x equals negative 3. If I need help to find the location of exactly the open circle where we need to locate them, just use, for example, to put it into the simplified equation 2 plus 1 equals 3. So the pair is 2 comma 3. So 2 comma 3. So this is the location of your first open circle. And then use negative 3 and put it into this negative 3 plus 1 negative 3 negative 2. So the coordinate is negative 3 comma negative 2. So this is the second hole or the second removable discontinuities. So this one is the graph of this particular equation. So you can quickly sketch this equation rather than you find the pairs like this one. So try to simplify it. Try to, again, if you find that the one that being left is a linear function, just graph the straight line, no, sorry, a linear expression. Just graph that linear expression first, and then don't forget that you have to include these removable discontinuities, since this is the thing that put a difference between this equation and this equation. Now, another example here, this is a rational algebraic function, and we don't know what kind of shape that we are going to have. But of course, you have to keep in mind that you can always use the table of pairs just like before. But now, since we have already learned about the previous two examples, so let's just not using the table of pairs, but let's just try to factor completely all both numerator and denominator, and then try to simplify, and then later we will figure out the simplified expression. So let's start with the factor completely. So if I use the factor theorem for the numerator, I will have these three factors on the numerator, and if I factor completely the denominator, these are the factors. So we can cancel actually one factor, one which is x minus 3, right? So let's just cancel it, and so this is the simplified expression, okay? But we have to keep in mind that x cannot be negative, s cannot be 3, right? Since if x equals 3, it will make the denominator equals 0. So if I simplify it, I try to multiply this. So we have actually a quadratic expression with, keep in mind that x cannot be 3. It means the shape of this rational algebraic function is a quadratic, is a parabolic, but with an addition that x cannot be equals to 3. So yeah, this is the result. So how to graph or sketch the rational algebraic function, you can refer to this equation and use all of the technique to sketch a quadratic function. For example, find the vertex. Using the vertex form, using the vertex formula, you can know that the vertex is negative 1, comma negative 1 here. And then find the x-intercept. Use the y equals 0 and then find all the x-intercept, which is for this one is negative 3, comma 0 and 1, comma 0. And then find the y-intercept. Y-intercept is 0, comma negative 3/4 or negative 0.75. So after that, you just sketch it. But don't forget, without the open circle here, actually this graph refers to this equation, not this equation. But to make this graph refers to this one equation, the original one, don't forget that we have to put the removable discontinue at the location of x equals 3 and the y equals, so you have to substitute 3 into this simplified equation, not into this, okay? Since if you put into this, of course, we'll have an undefined value, an undefined for your y. So let's just put into this and you will find that the value of the y is 3 also. So the location is 3 comma 3. So this is the location of your open circle. And yeah, this is the graph. So the graph is exactly the same with this curve, this parabolic curve of the quadratic function, but with an addition of an open circle here, since we are referring to the original one, this one. So you can conclude that again, you can use factor completely and then simplify it if the one that being left. So if the factors on the denominator is completely gone after you cancel it, you have, for example, a linear function, so the shape will be a straight line. But if you have a quadratic function, so the shape will be a, a parabola. And how to sketch it quickly? Of course, you need to recall back all things about quadratic function. How to find the vertex, how to find the x-intercept, how to find the y-intercept, and then sketch it. Don't forget to add the removable discontinuity, since of course we are talking about rational algebraic function. So for the last one, I will just give you some examples of a reciprocal rational function like this one, and then later I will show you two more. And I just show you the shapes, and then you can figure out how do you sketch it fast. Okay, this kind of rational function. So for example, we have rational function 1 over x plus x minus 3. Okay, since 3, you know that it's one of the prohibited x. Since if we put 3 into this equation, of course we will have undefined situation 1 over 0, which is positive infinitely large. Okay, so therefore, uh, 3 or x equals 3 will be one of the discontinuity. Okay, but it's not a removable discontinuity since we don't cancel x minus 3. Instead, the x minus 3 stays there, but it is on the denominator. It means it's still one of the discontinuity, but it is not a removable discontinuity. Okay, so what kind of discontinuity we are talking about now? It is a vertical asymptote. Okay, so the vertical asymptote is at x equals 3, the zero of this factor. So it is a vertical asymptote. Why? Because this asymptote will be a line where your curve will be getting closer, and from left and right it's getting closer but never touch. But in the end it will go to extremely large positive or negative, but it never touch. It's gradually come closer to this vertical line, but it just never touch. Okay, so that is the vertical asymptote. And then there is a horizontal asymptote also as well. So the horizontal asymptote is the x-axis itself. So when your curve is getting to the positive extremely large value of x, it's getting closer to the x-axis. It's getting closer gradually, but never touch. And if it goes on to the left, it will getting closer to the x-axis, but never touch also. So that is the graph of a reciprocal function. So how do you know the graph will be like this? Of course, the best thing that you can do is using the table of pairs. So for this one, I will skip it because the table of pairs is shown on the textbook, so you can just learn it. But by using the table of pairs, you can see that when you are getting closer to x equals 3 here, if you approach from the right, it will be somehow extremely changed into a large number when it's getting closer to 3. But when you approach from the left, if you go getting closer to 3, it will be extremely goes to the negative numbers, which is a very extreme one. But when it's getting further from 3, you can see that they gradually approaching the x-axis, but never cross the x-axis. So you can try yourself to plot this function by using the table of pairs, and you can figure out that there always be a vertical asymptote, depends on the zeros of the denominator. So it will be different with before because the factors are cancelled and then you have a removable discontinuity. But this one you don't cancel anything, but there is a factor that being left. This is the simplest one, right? This is the simplest form you can get, but still there is a factor on the denominator. So this factor has 0, which is 3, and that 3 will be another discontinuity, but it's not a removable. It is a vertical asymptote. So let's go to the second example. If I have this function, 1 over x plus 7, okay? So how to sketch it fast? First, since this is the simplest one, and I know that the denominator has a 0 that may cause the y value undefined, therefore we have another discontinuity, which is negative 7. So the vertical asymptote will be at x equals negative 7, so just draw the vertical asymptote. And then the rest will be just the graph will have a distinctive patterns. So on the right side, it might be like this and this. So if one is on the positive, the other one will be on the negative. But the curve is like this. It's getting closer to the vertical asymptote but never touch. And when it goes right, it's getting closer to the x-axis but never touch. If we go to the left part, it's when it goes further from -7, it's getting closer to the x-axis but never touch. But when it goes here, it approaching the vertical asymptote but never touch. Okay, but is it usually on? So, but the thing is, you cannot assume that always on the right side is the positive, on the left side is the negative, and so forth. Just to make sure is when you have the vertical asymptote, you have to up two alternative, which is this one and this one, the graph, or this one and this one. So to know which one is the correct one, to make sure, always use the pairs. So if I use, for example, -6 here, since -6 is the representative of the right area of the vertical asymptote, put into this and you have the value is 1 over 1. So when it is -6 for the x, the value of the y is 1. So this is one of the pair. Therefore, the curve on the right must be at the positive on the positive section above the x-axis, above the x-axis. So this must be the curve. And on the left side, if I, for example, I use -8 and I put here -8 into the x, I will find the value of y is -1. So -8 comma -1 is one of the pair. So I know that the rest will be under the x-axis. Why? Since this curve will not pass the x-axis. The x-axis is the horizontal asymptote. And when it goes here, it never passes x equals -7. So that is how the graph of this kind of reciprocal. The last one. So this one is different. Look, this one on the right side is above the x-axis, on the left area is below the x-axis. But this one, the left area of the vertical asymptote is above the x-axis, but while the right area is below the x-axis. Why? So let's just try to figure out how do you find the vertical asymptote. Use the equation, of course, since the denominator has one factor that cannot be cancelled, cannot be eliminated. So we have another discontinuity, which is a vertical asymptote. The 0 is 5. So x equals 5, this is the vertical asymptote. So the next question is, before you figure out the graph, whether the graph will have on the right side above x-axis and on the left side below x-axis, or on the left area of the vertical asymptote above the x-axis and the right area below x-axis. So just use the representative. Since this is the vertical asymptote, so on the right area, I can use, for example, 6 as my representative. If I put 6 into this equation, I will find the value of y is -1. So -1 is here. It means the graph or the curve on the right area of your vertical asymptote will be below the x-axis. And the one that is on the left area of the vertical asymptote, you can just check by using 4 as the representative. Of course, you can use 3, 2, 1, 0, and so forth, but for this one, I will use 4. And then I put into this, so I can find that the pair is 4, 1. So it is here, one of the pair. It means the curve will be like this. See, when it goes further, it's getting closer to the x-axis, but never touch again. It's just by faith, we know that it's gradually getting closer, gradually. So it never, there is a state of a horizontal line that stays on the same level. No, it's gradually getting closer. Okay, so that's the graph of reciprocal, and that ends our explanation.